the way you love me all the time. Or maybe I'm afraid of the way I love you. Maybe I'm amazed at the way you pulled me out of time. You hung me on the line. Maybe I'm amazed at the way I really.
Okay, today we're going to finish off chapter 2. We're going to do section 2.8, which is called higher derivatives. So what we've done over and over in this chapter is we've taken the derivative of functions. And we've also seen that when you take the derivative, you get a function. The derivative is a function itself. So because we can take the derivative of functions, and the derivative itself is a function, it follows that we can take the derivative of a derivative. So that's what we're going to do today. We're going to take derivatives of derivatives. So we've so far done the first derivative. When you take the derivative initially, it's called the first derivative, and we've seen that this can refer to two things, right? I'll just write them up here to remind you. The first derivative can refer to the slope of the tangent line, and it can also refer to the instantaneous rate of change. If we're talking about position of some object, which we did quite a bit, remember we were talking about velocity. The first derivative gave us the velocity. So let's go on to the second derivative. The second derivative doesn't tell us about velocity, it tells us about the change of velocity over time, which can be interpreted as acceleration. So remember, velocity is the change in position over time. If we take it another step, and the change of velocity over time is acceleration. Second derivative can also be interpreted as the rate of change of the slope of the tangent line. So the first derivative gives us the slope of the tangent line. The second derivative gives us the rate of change of the slope of the tangent line. How fast is that slope changing? It can be denoted in several different ways. Usually you'll have one of these two. You'll either say y not prime, but prime prime, y double prime, right? Or it could be f of not prime x, but f double prime of x. These both mean take the second derivative. Instead of dy dx, you could have d squared y over dx squared. And the last way, which I have to admit I've very rarely seen, is capital D squared of f of x. Again, the ones that are most common, I would say, are these two, although I do remember seeing the third one a fair bit at university as well. But I'm going to stick to these two this year probably. Okay, the third derivative. First derivative was velocity. Second derivative can be interpreted as acceleration. You ready for the third derivative? It can be interpreted as jerk or jolt or lurch. So it's kind of how fast is the acceleration changing over time. It's getting pretty hard to picture. It's not really that useful of a concept for most people unless you're, I don't know, dealing with car engines or something like that. But that is the technical term, is interpreted as jerk. You don't need to worry about that in this course, but I put it here for interest's sake. It can be denoted by, you can probably guess, since this was y double prime, y triple prime. This could be f triple prime of x, and this could be d3y over dx cubed, and this could be d cubed of f of x. So pretty straightforward probably. The fourth derivative, we've gone from velocity to acceleration to jerk to jounce or snap. I mean, it's hard to even picture what this means. The rate of change of jerk over time? I mean, I don't know. Don't worry about it. Just last year when I taught this course, the kids really wanted to know what it was for the third and the fourth and fifth, so I looked it up. There's not even universal agreement about this, I don't think, but this is what I found. How do you denote those? Well, you're probably guessing what you would do is you'd go y prime 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 prime. Don't do it. Sorry, you probably did. What you do once it gets this high, you don't put all those ticks because we don't want to bother counting them all. You put y with a 4 in brackets. That's equivalent to doing tick 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 tick. Same with f 4 in brackets of x, and these are just as you'd assume: d to the fourth y, dx to the fourth, and capital D to the fourth of f of x. Okay, by the way, just to really complete this is absolutely ridiculous, but again, I did find this in multiple places. So the fourth derivative can be called snap. Guess what the fifth one and sixth one can be called? This is ridiculous. snap, the 5th could be crackle, and the 6th could be pop. I kid you not, I have found that in multiple places. Completely useless for us. We're never going to be talking about snap, crackle, or pop in this course unless someone brings Rice Krispies in one day. Please do. Okay, so the nth derivative, whether it is the 5th, the 9th, the 12th derivative, whatever, you could represent how? Well, you could say y to the nth power, f to the n power of x, dny over dxn, and capital D to the n of f of x. I mean, that should be pretty common sense if you got the pattern in the previous ones. Okay, so you might still be confused. What exactly are we talking about with these second derivatives and third derivatives? Happy news, it's really quite simple. So what we're going to do here is we're going to start by taking the first derivative. That's what you have to do to get the second derivative. You have to start by taking the first derivative. So let's do that. We'll take the first derivative. How do we do that? We're going to use the power rule a whole bunch of times. So we're going to bring the 4 down, you get 4x cubed. We're going to bring the 3 down, you get 6x squared. Bring the 2 down, you get negative 10x. Bring the 1 down, I guess, you get plus 3. This is a constant. There's nothing to do. Okay, now what we want to do, since we got the first derivative, we want to take the second derivative. How do you do that? You take the derivative of the first derivative. And how do we do that? Power rule again. Bring the 3 down, you get 12x squared. Bring the 2 down, you get 12x. Bring the 1 down, negative 10. This is a constant. There's so that just equals 0. Okay, that's the second derivative. Let's go to the third derivative. Get the pattern, you just keep doing it to the previous one. Power rule again, 24x plus 12. This is a constant, equals 0. Okay, fourth derivative. Remember, we're going to write it like this. Take the derivative of the third derivative. So you get 24, and this is just 0. We're done. Fifth derivative. Take the derivative of 24. Well, that's just a constant, so the derivative is 0. What if it was a sixth derivative? Still 0. Seventh derivative, 0. 28th derivative, 0. From now on, they're all going to be 0. And that's basically all you need to know about higher order derivatives. Let's do a couple harder ones. So this one, we're going to use implicit differentiation to find y double prime. Remember, implicit is what we did last day. So we're going to take the derivative of both sides in terms of x. First of all, we'll take the derivative of x cubed. So use the power rule here. 3 comes down, you get 3x squared. Derivative of y cubed, again, move the 3 down, you get 3y squared. But because this is implicit differentiation, right, you have to slap a y prime on here, or a dy dx, because we're taking a derivative of something that includes y. Equals, now you need to take the derivative of 5, which is just a constant. And when you take the derivative of 5, you get 0. Okay, the next step in implicit differentiation was to get that y prime all by itself. So why don't we leave this term over here, but move this term, the 3x squared, over to the other side, and it becomes negative 3x squared. Last thing to do to isolate the y prime, divide both sides by 3y squared. So you're going to get negative 3x squared over 3y squared. Can cancel those 3's, so you'll get, if I cancel those, I get negative x squared over y squared. So great, that's what y prime equals. But now I need to get y double prime. So here we go, y double prime, second derivative. How do we do that? I take the derivative of the first derivative. So I'm taking the derivative of this. Well, wait a minute, how are we going to do that? We're going to have to use the quotient rule here, aren't we? So quotient rule says you take the derivative of the top, which is negative 2x, and you multiply it by the bottom, y squared. Then you subtract, and what you subtract is the top, which is negative x squared, times the derivative of the bottom. Well, the bottom is 2y, and since it involved a y, I got to slap a y prime on there. All over the bottom, which is y squared, squared. Yeah, that is the quotient rule. Let's simplify that a little bit. So I think we'll just keep that first term the same. We have a negative and a negative, so it becomes plus, and we'll have 2x squared y prime over y squared squared is y to the fourth. Okay, now what do we do? I mean, this is what y double prime is, but it's pretty complicated. Well, you see this highlighted bit right here? this is what y prime equals. And we have a y prime right here. So where it says y prime right here, we can plug in that negative x squared over y squared. I know you don't want to because it's going to be pretty ugly, but that's why actually what you have to do here. So I'm going to put sub in, like substitute in to that spot right there. So now what I'll have is y double prime equals, I'm just going to rewrite all this except for that highlighted bit. So I'll have negative 2x y squared plus 2x squared y, but now I'm not putting y prime, I'm putting negative x squared over y squared, and that's all divided by y to the fourth. And we got to simplify that. So let's start by keeping this first term the same, negative 2xy squared. Okay, this is multiplying here. So you can cancel this y with one of those y's. And it's going to be negative, isn't it? Because we got 2 times negative 1 here. So you have minus 2. You're going to have x to the fourth power now. X squared and x squared gives you x to the fourth. And it's over y. And this is all over y to the fourth. Okay, let's get the numerator, like this big numerator up here. Let's get that with the common denominator. Well, this is over 1, so we have to multiply top and bottom here by y. Our common denominator is y. So we will have negative 2x y to the third, we've got one more y there, minus 2x to the fourth, all over y. And we're going to divide that by y to the fourth. But dividing by y to the fourth is same as multiplying by the reciprocal, which is 1 over y to the fourth. Okay, so now what we can do, on the top, why don't we factor out, what can we factor out? Negative 2x. Take out a negative 2x, and what's left is y cubed plus x cubed. And on the bottom, we have y times y to the fourth, which is y to the fifth. Seems like we're done, doesn't it? But here's something that will often happen, and it's kind of a cool thing. If you look at this right here, y cubed plus x cubed, and you look back at the start here, y cubed plus x cubed plus y cubed, they're exactly the same. So we know that highlighted part in green down there must equal 5. Since x cubed plus y cubed equals 5, then y cubed plus x cubed also equals 5. So we can return this into negative 2x times 5 over y to the fifth, which means y double prime, our final answer is negative 2 times 5 is negative 10x over y to the fifth. That is what the second derivative of this particular question is. Okay, that was a very complicated question. Okay, so we're going to get the second derivative of this function, and notice it's f double prime of 1. So remember what that means. It means we're going to find the second derivative, and then we plug 1 into it. So we don't have to get it in quite as much simplified form as if it was just f double prime of x, because we can plug in once we have the second derivative. So how do we do this? Well, we start by getting the first derivative. So what rule are we obviously using here? We're using the chain rule. Our outer function is something to the 10th, and our inner function is 2 minus x squared. So start with the outer function. 10 comes down, leave the inner function alone. Power rule says this becomes a 9, and then we multiply by the derivative of the inner function. Well, the derivative of the inner function is just negative 2x. So I might as well simplify that. That'll make our second derivative a little bit easier. So 10 times negative 2x is negative 20x, and then we multiply that by 2 minus x squared to the 9th. Okay, time to find our second derivative. So which rule do you need to make sure you're using here? You'd better use the product rule. We've got two pieces here. Here's the first piece is right here, and the second piece is here. So product rule, the way I like to do it is to start by taking the derivative of the first term. So that would be negative 20, and we multiply that by the second, 2 minus x squared to the 9th. Plus, we just rewrite the first one, negative 20x, and we have to take the derivative of the second. Well, we've got to use the chain rule again. 9 comes down, inside function stays the same, 2 minus x squared, 9 drops down to an 8, and we're going to multiply, don't forget, you got to get the derivative of the inner function, and that again is negative 2x. Okay, I say we simplify just a little bit. Let's keep this the same, the negative 20. You can just plug in right now, but I'm going to simplify just a little bit. So we have negative 20x times 9 and also times negative 2x. So negative and negative means we're going to have a positive. 20 and 9 is 180 times 2 is 360. And then we have x and x is x squared. And what we still have is 2 minus x squared all to the 8th power. So you're ready now to plug in. You can simplify more if you want. If you want to see how you would do that, like if the question was just find f of double prime of x, what I would do now is I would take out a negative 20, and I would also take out a 2 minus x squared to the 8th, right? And then what you'd be left with is, in the first part here, you'd be left with another 2 minus x squared. For the second piece, that's this piece here, you would need to have what? Negative 20 times what equals 360? Negative 18. Then you'd have an x squared, and you wouldn't have any 2 minus x squareds because you got them all here. So that'd be it. And then you would have negative 20, 2 minus x squared to the 8th, and in here you would have 2 negative x squared, take away another 18 squared is minus 19x squared. So, that was a couple extra steps that were kind of a drag, a little bit difficult maybe. So you didn't have to do those in this case. If it just said f double prime of x, yeah, you should definitely do that. That'd be the answer I'm looking for. But if it just says this, f double prime of 1, you could have plugged 1 in right here. So let's do it. And it's so nice, as I said before, when they give you the value of 1, because if I'm doing f double prime of 1 and I'm plugging in here, I get 2 minus, well, 1 squared is just 1, 2 minus 1 is 1, 1 to the 9th is 1, 1 times negative 20 is negative 20. Okay, and then we put 1 in here. 1 squared is 1 times 360 is 360. 2 minus 1 is still 1, to the 8th is still 1. So I get negative 20 plus 360, which is 340 is my answer. Want to double check or show that it works even if you did it here? If you put, so I'll just write the same thing. If you put 1 in here, 2 minus 1 squared is 1, 1 to the 8th power is 1, negative 20 times 1 is negative 20, just like we had here. So 1 squared is 1, 19 times 1 is 19, 2 minus 19 is negative 17, and negative 20 times negative 17 is 340. We get exactly the same thing. So it doesn't matter which way you do it, but hey, if you know what you're plugging in, especially if you know you're plugging in a 1, which makes it so easy, I would probably have done it back here, but you do need to know how to get down to here in case it was f double prime of x. Make sense, everybody? I hope so. This ends chapter 2. This is probably, of all the chapters in the course, the one you must absolutely master to have success in this calculus course and in your calculus course next year as well. All right, learn it, love it. See you soon.
Baby,